Okay, welcome to lecture 13 for ECE 203. Today we're going to kind of wrap up what we've seen about the DFT, or the discrete Fourier transform, and we're going to tie the DFT and the spectrum that we draw using the DFT back to the spectrum of the original continuous time signal, and show that in certain scenarios it looks similar, and in certain scenarios it looks the same, and in all cases it looks very similar. Okay, so like I said, the question we're trying to answer is, how does the spectrum computed with the DFT compare back to the original continuous time signal? So to study this, we're just going to consider the continuous time signal, our favorite continuous time signal. X of t equals some amplitude times cosine 2 pi f naught t plus some phase phi, right? And what we've seen is that we can just draw the spectrum of this. Normally we would expand it using Euler's identity, right? And we get this a e to the minus j phi over 2 at a frequency of minus f naught. And then we would also get in a e to the plus j phi over 2 at a frequency of positive f naught. And f naught is in hertz. So let's imagine we have this continuous time signal, and we decide we're going to sample it at a sampling rate, fs, that's greater than twice the maximum frequency component, which is just the frequency of the sinusoid. And we're going to do that for capital T seconds. All right, so then we obtain the following discrete time signal, right? We have x of n equals, again, this amplitude, right, times cosine 2 pi f naught n over ts plus phi, right? All we did there was we just set x of n equals x of n times ts, where ts is the sampling period, and that's that's defined for values of n from 0, 1, 2, dot, 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 all the way up to n minus 1. Okay? And here, since we sampled for capital T seconds, then if you thought about this a while, you'd say, okay, well, capital N should be about capital T times Fs. And more precisely, it's going to be the floor of capital T times Fs plus 1. Okay? So now we have this, again, we have this discrete time signal x of n. It's just a cosine, and say it's at some digital frequency f naught of f0 hat. Okay, so we're f0 hat. To remind everybody, f hat was defined as the frequency divided by the sampling frequency. Okay? Frequency of the sinusoid divided by the sampling frequency. So this is just all to remind people how we drew the spectrum and then how we sample the signal. So we have this continuous time signal x of n, and now we want to compute its spectrum using the DFT. Let's go ahead and write out the definition of the DFT. So I have that right here, where the signal x of n is written in green. So the definition of the DFT is just that sum, right? So this, say x, capital X of k is equal to the sum from n equals 0 to n minus 1 of x of n times e to the minus j 2 pi k over n times n. And so now I've just already inserted for x of n, I've just inserted that discrete time sinusoidal signal. Okay? And then the first step, I'm just going to break everything apart using Euler's identity, replace cosine with our Euler's inverse identity for cosine. Right? And that's how I get this second line. Nothing tricky yet. And then I'm just going to kind of split up this sum. Right? I'm going to factor out the a over 2 e to the j phi, right, because that doesn't depend on n. I can just bring that outside of the sum. That's this term. And then I'm going to do the same thing for the components on the right. I'm just going to write those as a different sum and then pull out a over 2 e to the minus j phi. So to go forward, let's only look at this first term, just to kind of simplify things. Okay, so by first term I mean this guy. Let's only look at this first sum just to make things a little bit easier. And I want to remind everybody an identity for a geometric series. Okay? And what that identity is if we have a sum of some number alpha raised to the n, and we're summing over the index n. So that would be, for example, if alpha were 1/2, then I could just write this. This sum would be equal to 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus ... Right? And so there's a nice formula for that, and that's just what's written right here. That's 1 minus alpha raised to the capital N divided by 1 minus alpha. So in the case where alpha is 1/2, if we sum up these components from n equals 0 to capital N minus 1 of 1/2, we would just get 1 minus 1/2 to the n divided by 1 minus 1/2, which is just 1/2. Okay? That's just to remind everybody how that identity works. And so this doesn't only apply to real numbers. So we can actually put in a complex number alpha, and it's pretty convenient that we have this identity because we can just apply this to these two sums that we have above. All right, so let's go ahead and do that. And now remember, I'm just going to consider this first sum, and now I'm summing again from n equals 0 to n minus 1 of this complex exponential times n. So I can rewrite this as the sum from n equals 0 to n minus 1 of alpha raised to the n, where alpha is defined as e to the minus j 2 pi f naught hat minus k over capital N. Okay. So I've just defined alpha to be this complex exponential without this n term, right? And remember, we're summing over n, so then we just plug in this value of alpha into there. That's the sum we're looking at, right? And so now I'm just going to go back up to this formula here and plug in this particular value of alpha. And that's what we have written here. Okay? So we have this fraction, and it's 1 minus a complex exponential, right? But that complex exponential is kind of raised to the capital nth power, and then on the bottom we just have 1 minus the complex exponential. Okay. So let's kind of continue down this path and see where this leads us. Before we do that, let's write out the whole expression. So now I've just gone back to the definition of x of k, and I've used this identity, used this trick, using this alpha trick, and I have two terms. Right? Before I was only considering one term. The second term is use the exact same trick, and then you see you get this kind of rather complicated large expression that's at the top of the screen. So for now, let's just assume that f naught hat is just equal to L divided by capital N. And what I mean by that is L is some integer. Okay, so L could be 1, 0, 1, 2, 3, ... But it's also less than capital N over 2. And then let's kind of take a closer inspection of this first term written here, this first black term. Okay. So when we inspect that closer, we see the following. You can see that if we look at the terms where k is not equal to L, right? If k is not equal to L, then we get on top, we get these, we always have this n cancels, right? This n cancels with this n. But now k is not equal to L. Okay, so k is not equal to L, then we just have another integer here. Say maybe the integer is m, where m is defined to be k minus L. Okay. And we always know that e to the j 2 pi times an integer is always equal to 1, right? You write that out. E to the j 2 pi times m, where m is an integer, that always equals 1, just by Euler's identity. Okay, so on the numerator here, we just have 1 minus 1, which is 0. All right, so we're almost ready to write that for scenarios when f naught is equal to L over n, so when the digital frequency is some integer divided by n, and for values of k such that k minus L is 0, aka if k is equal to L, then this numerator is 0. Okay, now the denominator in that case, again, k minus L here would just be some, this gives us m, we get m there, and then on the denominator, in this capital N here, right, there was no other n to cancel this with. So this value is just actually some number less than 1, right? So we're making the assumption L is less than n over 2. This is actually less than 1/2. Okay, so we have e to the j 2 pi times some number, and that's never equal to 1 unless k is equal to L. So that denominator is always non-zero if k is not equal to L. So then we can just conclude from all that we get this first value. When k is not equal to L, this fraction written here is equal to 0. Now when k is equal to L, it's a little trickier. Right? When k equals L, then if we just evaluate this, we get something like 1 minus e to the j 0 divided by 1 minus e to the j 0. Right? K minus L is 0. Both of these exponents, right? This is 0. This is 0. So we have two complex exponentials with 0 in the exponent. We have 1 minus 1 divided by 1 minus 1. So it's not defined. And we saw this kind of the same issue for Fourier series. All right, so how do we continue? Well, in the same way we did for Fourier series, we go back to the definition, right? Go back to the definition of what capital X of k is, and let's just look at, maybe I'll go back one page, right? Go back to this sum here before we use that trick with alpha, okay? All right, so I'm just going to rewrite that sum on this following page, right? That's just written right here. And now we're saying when L is equal to k, then we have the sum from n equals 0 to n minus 1 of 1, right? This evaluated again at e to the j 0 is of course 1. So we have the sum over 1, and we add those all up, and that just gives us capital N. All right, so we're done with the first term, right? We have kind of two things now. We have the case when k is equal to L and when k is not equal to L. And so we could do, kind of play these same tricks now for the second term, this term written here. And when we do that, we see essentially the same thing, except now, and I won't walk through this one in as much detail, but when k is equal to capital N minus L, then we get a value of n. If k is not equal to n minus L, then we just get a value of 0. So it's a lot like the Fourier series, right? And what we're saying now when we bring this all together is the following. We have, if provided f naught hat, let me fix this quickly, provided f naught hat is equal to L divided by capital N, where L is some integer, then I can write the DFT of x as follows. It takes on two non-zero values, okay? And one of those non-zero values is for when k is equal to L, then we just get this positive a over 2 e to the j phi, and then when k equals capital N minus L, we just get x of k equals a over 2 e to the minus j phi times, of course, times n for both of these, right? Where we just, that n came from just back on this page where we had this sum, okay? So all we did is just looked at these specific cases of this equation here, right? And then we're able to write out the cases in actual expression for x of k. And so this is interesting. This is kind of what we expected, right? So remember the original continuous time signal. If we now plot this capital X of k, the DFT coefficients like the spectrum, it looks a lot like the spectrum of the continuous time signal. One thing you might say is, well, now there's this extra factor of n here. That's really just arises because of the convention that the DFT is defined as it is. It has a scaling 1 over n for the expression for when we synthesize lowercase x of n. Okay, so the spectrum looks the same, right, which is good. And remember how we plotted this, went through this last time, but we just drew the values of x of k. And normally you could draw the spectrum from starting at k equals 0 all the way up to n minus 1, right? But remember we wrapped around those values. In MATLAB that would be what we call the command FFT shift. All right, so here's the plot below is just kind of shows that exact same picture. Here's the value k equals 0, right? Here's the value L, and here's k on this axis. So again, L tells us the digital frequency, right? So, you know, one thing we really kind of glossed over here was what happens if f hat is not kind of this integer multiple. And then we run into something called spectral leakage, okay? So we have, you know, I'm showing this picture on the screen, and you can kind of see this green plot in the background. That's going to make a little more sense on the next page. But for now, just think of this as what we've seen is that when f naught hat is equal to L over n for some integer L, then the spectrum looks exactly like it did for the continuous time signal. Okay, so let's kind of take a step back and again look at that expression for x of k. Remember we had this general expression for x of k before we plugged in. Remember on the last slide we took the same expression and we plugged in f naught equals L over n. So we're not going to do that now. We're going to say f hat is not equal to L over n. And so we can't really plug anything in here. We can't really simplify this a whole lot more. So what's happening here is that this f hat, put a hat on this guy, is not an integer multiple. We can't just write it as some integer divided by n. Like I said, we can't simplify this expression much more. And then in that case, there's no sinusoid in the DFT that somehow perfectly matches up with the signal x of n. So what we have to do is we end up using all of the DFT coefficients. There's none of the DFT coefficients are 0 in this case. And again, we can see this, this green plot in the background. That corresponds to this signal plus this signal here. Okay? And what we're seeing is we're somehow sampling that. So that green signal is that the sum of those two as a function of now set k equal to be a continuous valued random variable. And then you get this green plot in the background. And what's happening is if we were somehow perfectly lined up, meaning if f hat, which is this peak is f hat, if f hat happened to be at an integer divided by n, then we'd be sampling right at the peak. And all the subsequent samples that weren't at the peaks would be actually in these valleys. They'd be all be 0. So this concept is called spectral leakage, and this is the reason why that a lot of times when we take the DFT of a pure sinusoid, we don't actually see a perfect spectrum like we'd expect to see if we just looked at the continuous time signal. Right? And again, that happens because the sinusoids in the expression for the DFT don't perfectly match the signal x of n. Right? Remember that the sinusoids in the expression for the DFT were at frequencies 1 over n, 2 over n, 3 over n, so on. And if our original continuous time sinusoid doesn't correspond to a digital frequency of one of these values, then we need to use more than just a single sinusoid to